Hey everyone, welcome to the inaugural episode of the EduHaven course on AP Calculus AB and BC. If you're ready to succeed, let's go. If you've ever taken an algebra course, you may have heard of the average rate of change. The equation for the average rate of change looks like this. Notice the change in x value on the bottom. In order to take the instantaneous rate of change, you have to make the change in x smaller and smaller, or approaching zero. Now, how do we make the denominator smaller and smaller, approaching zero, without making the equation undefined? And the answer is limits. A limit returns the value that a function is approaching as the independent variable approaches a certain x value. For example, with this function, the limit of f of x as x approaches 2 is 3. It's important to note that this independent variable is not always x. Limits can be found in multiple ways. For example, with a table, you just see the value that the function approaches as it approaches a certain x value from both sides, like this. You can also find a limit using a graph. With a graph, you just see the function value as the x value approaches a certain value. Like with this function. This function is called the octopus function. Limits in general are typically taken from both sides. However, one-sided limits can also be taken. When a plus is written, you're taking the limit from the positive direction, typically from the right. When a minus is written, you're taking the limit from the left, or the negative direction. Now, let's do some properties of limits. First, the limit of a constant is always the constant. Next, the limit of a sum is the sum of the limits. The limit of a difference is the difference of the limits. The limit of a product is the product of those limits. The limit of a quotient is the quotient of those limits. The limit of a constant times a function is just the limit of the function times the constant. The limit of a function raised to a certain power, also called a rational function, is the rational power to the limit of that function. That can also be seen like this. A lot of these properties are simple and can be easy to memorize because they follow a mirror-like pattern. Limits of piecewise functions or functions with multiple parts are like normal limits but with the specific part like this. To understand the limits of piecewise functions, you have to understand continuity. Not video consistency, but this rule. Put simply, this just means that you can draw a function without lifting up your pen, like this, but not like this. However, the limit of a piecewise function as the x value approaches the value that the functions change is only equal to one of the functions if the limit from the right of the right function is equal to the limit of the left. For evaluating limits of a polynomial function like this one, or this one, or this one, you didn't put anything down there? Oh God! As I was saying, like this, or this, you may start to see a pattern emerging. You're able to just plug in the x value into the function, or you can just see the y value of the function at that specific x value that you're approaching. However, there are a few instances in which limits do not exist. Firstly, when plugging in for x and it results in an undefined function, the limit does not exist. Additionally, if the limit from the right and the left is two different limits, the limit does not exist. This can also be called a jump discontinuity. Lastly, if a limit oscillates over a certain value, it does not exist. However, when you plug in the value that you're approaching into the function and it results in a 0 over 0, this is a special case called a removable discontinuity. This just means that there's a single hole in the graph. However, the limit as it approaches this removable discontinuity doesn't necessarily mean that it doesn't exist. Put simply, a removable discontinuity like this one, the limit does actually exist, although it's only approaching that value and doesn't actually hit that value. If you find the 0 over 0 when you plug in, there's multiple ways of trying to solve for the limit. First, you can try to factor and cancel out expressions like this, where you cancel out the x minus 4. You can also multiply by the conjugate. The conjugate is like a difference of perfect squares, but only one part. This is usually used to clear up a radical, and can be seen like this. You can also multiply by the LCD, or the least common denominator. With this example, you multiply by 3 times 3 plus x, which results in a limit equaling -1/9. Finally, you can substitute with identities. Typically, these are trigonometric identities. The most important one that I would say is sine squared x plus cosine squared x equals 1. However, this is where your pre-calculus knowledge comes into play. For example, with this function, it results in a 0/0 when plugging in for x. This means you have to use this identity. When plugging in, it simplifies to this. Finally, you can evaluate the limit using this equivalent function. However, it's much easier this time, and you get this answer. The thing about the AP exam is that there are very few limit questions because it's only 1 unit out of 10 units. This means that you may or may not need this knowledge. However, it can always be helpful to supplement your knowledge. For me specifically, I only memorized the major trigonometric identities, and you can find a link to them all in the description. Now, that's a starting point for Calculus AB and BC. If you want to check out another episode of this course, click right here. If you want to check out another EduHaven course, click right here. Thanks for watching, and I hope you succeed.